We're talking with Dr. Robert J. Nemiroff, whose new book, Faster Than Light, How Your Shadow Can Do It, But You Can't, tackles some really big questions, the kind that when you think about them, hurt your brain. I mean, where does the universe end? And if it ends, I mean, what's on the other side? What existed before the Big Bang? Is there a scientific engineering concept that would allow us to sidestep the obvious problems with traveling faster than light across the universe, never get there? Is retrocausality real? Can the future intervene and affect what goes on in the present? A lot of fun stuff here, and we're going to jump right into some of those big questions right after this. Robert, let's jump into some cool stuff here. Entanglement, spooky action at a distance, what Einstein called it. Is that related to the speed of light? I mean, how could two particles on opposite sides of the universe be connected somehow? I have a hard time getting my head around that one.
Yeah, that's pretty interesting. But if you would allow me to build up to that with a digression or two, which I think that your coast-to-coast audience would appreciate.
Sure.
So the speed of light we know now is constant. So whatever you see out there, you're not seeing it as it is right now. You're seeing it as it was in the past. So that thing across the room, that's not the way it is right now. That's in the past. That car out there, no, it's a little bit different maybe now. You're seeing it in the past. When you look into a mirror, you don't see your present self. You see yourself as you were in the past. Now, it's a very, very slight fraction of a second in the past, but you can fix that in theory by moving the mirror far away. So in theory, if there was a mirror far enough away, and if you could see it, you could see yourself as when you were a child.
I wish.
There's nothing against the law of the physics. That's what the laws of physics predict. So far enough away. In fact, light circles around a black hole. So in theory, if you could have a big enough telescope and decode the radiation enough, there's images of yourself when you're a child that circled a black hole and are on the way back now, but we just don't have the technology to see it. So you can only see the past. And one of my favorite phrases is, which I think I use in the book, is you can only see the past, but you can only predict the future. And there's another really cool thing that comes up in the book, too, is that even though you can see yourself in the mirror, you're not really seeing your true self. Most people have never seen their true self. Now, what do I mean by that? What I mean by that is that the air re-radiates. You see yourself through air, and air re-radiates a version of you. This is an effect that was actually discussed by Ewald and Osteen in 1915. There's something called the extinction length. So the extinction length of the light that you emit that we see in air is only around a millimeter or so. So if you look at yourself in the mirror, you're not seeing your true self. You're seeing a re-radiated version of yourself through the air. And through water, it's even less. So you have to really put your eye right up to your skin to see a little bit of yourself for the first time. So I just thought I'd hit some background with that. I thought your coast-to-coast audience might appreciate that.
Yeah. We've had guests who look at reality existing only for the benefit of the observer. That I think you wrote that the moon would still be there even if we weren't looking at it. But I sense that you give some credence to the observer effect. Am I wrong?
Yeah. So what we see can be very different from what we consider to be objective reality. Subjective reality, we build up objective reality from all of our subjective observations. And we say, okay, I'm seeing this, and this person's seeing that, and let's put this all together and figure out what objective reality is. And usually we can do that. There's some really strange cases where it's not really clear how to build objective reality from what people see. And one thing is about these spots that move faster than light. So if you have a spot moving toward you, a laser spot moving toward you on the wall, faster than light, which can happen, there's only one spot in this case moving toward you. But what you see is when that spot toward you, when the speed of that spot toward you drops from the speed of light toward you to less than the speed of light, then you see what's called a relativistic image doubling event. You suddenly see a pair of spots, and one goes one way and one goes the other. Because before, when it was moving toward you faster than light, it was preceding the light. So then when it dropped to lower than the speed of light, the light precedes it. And so the way that you see that is that you see a pair of spots just go off in different directions. So that's what you subjectively see. But from that, you can build up the idea that there was just one spot moving across faster than light. This is one of the surprising things that can happen with speed of light type stuff. It's just there's a lot of surprising concepts there, and I'm always surprised. I sometimes stumble across another one, and I say, "Really? Wow!" And again, what is objective reality? All we see is subjective reality, and subjective things are different. For instance, just the Doppler shift. So a car moving toward you sounds higher pitched than a car moving away from you. So those are just subjective hearing of what a car is. But objective reality might be considered the sound that car makes or the car horn makes that doesn't have the Doppler shift moving toward you or away from you involved in it. So what we do is we say, okay, I hear a car moving toward me. I hear the sound of the horn. I now know that it's moving toward me, so the sound of the horn is a higher pitch than it really is. So I reconstruct objective reality. The sound of the horn is there's actually a little bit of a lower tone there. And then I know that when I speak with somebody else, I don't tell them what I heard because that's just me. I tell them what it is, that sound that was being emitted by the car in the car's own frame. And they can say, oh, yeah, I can reconstruct that as well. So, yeah, this objective reality thing, it's there. We can reconstruct it from what it is we see. And what we can see sometimes can be very strange.
Dark matter and dark energy, those both strike me as strange. I mean, is there a way where the speed of light calculations help us understand those? And by the way, where the heck are they? Why haven't we found them?
Okay, so yeah, dark matter and dark energy, I don't think they're directly related to speed of light effects, although we see them across the universe, and it takes light a long time to get to us from there. So, yeah, turns out in the last, 50 years, last 20 years, in fact, looking at distant galaxies, we found out that they're moving away faster, and also galaxies inside, stars moving inside of galaxies, they move strangely. Galaxies moving inside of clusters of galaxies, they move strangely. They're moving strangely fast. And so what is it? What gravity must hold them in there, these stars moving around our galaxy? And so either the theory of gravity is slightly wrong, which many people believe, or more popularly, there's something called dark matter there that emits gravity like regular gravity that we're used to, but we don't see the light from it. So the stars moving in the outskirts of galaxies, they're not only responding to the light from the mass that we see from the light that it emits, but they're reacting to matter we don't see. So that's called dark matter. And a good fraction of the universe is thought to be dark matter, which is different from mostly the matter that we're made out of. But besides that, in more recent times, we've seen that galaxies are moving away from us faster than we can explain. And so we now think that there's something even more strange than dark matter, and that is called dark energy. And this is a gravitationally repulsive force or energy that we didn't really know. We still don't know what it is. What I like to think of is that if you go back 1,000 years, people don't know almost much about air. They know a few things. They can say, oh, look, that leaf is fluttering because of air. I feel wind because of air. But we really didn't know much about air. We would have thought that the most massive things are the objects that you see, that rock over there or something. But it turns out that collectively the air between you and the rock probably is more massive than the rock. And now we know air is there, and air is very interesting. Air is made of oxygen and nitrogen, and oxygen is really important. It helps us. We breathe in. Well, we breathe in all the air, but the oxygen is really important for us to survive. But we didn't know that 1,000 years ago. We just knew there was something called air. So now with dark energy, we know there's something out there called dark energy, but we don't know much about it at all. Maybe if we know more about it, there's things that are like oxygen about it. There's things that allow us maybe to move in ways that we can't picture now. Right now, we think that locally we're confined to the speed of light, but we know that distant galaxies are expanding out far away from us faster than light. So maybe there's a clue for that if we understand dark energy. And tying it back to the beginning of the show, maybe we'll learn more about that with the James Webb Space Telescope might tell us more about that.
It gets pretty lonely, the feeling, when you read your book, in the sense of the universe expanding and galaxies going away from us faster than the speed of light. I mean, if we were still around in billions of years, or maybe more than billions, it'd be awfully lonely because we couldn't see any other galaxies, I guess.
Well, so galaxies, right in objective reality, some galaxies far away, they're so far away that we will never reach them. But they emitted light in the past that we can see. So we can still see those distant galaxies. We can see an increasingly dim and red version of them, sort of frozen in time. But so we're always going to be able to see the microwave background, which is the early part of the universe, and distant galaxies. But that's because the light we see took a long time to reach us. So, but right now, if we could go to where they are right now, yeah, they're out so far that we can't communicate them. If we were to take our laser pointer and shine it at them, they'd never see it.
The size of our universe, you wrote that for all intents and purposes, it might as well be infinite to us. Is it infinite? I mean, and if there is an end to it, what's on the other side of that?
Okay, so we just don't know. We're on science scale. So humans know things on human scale. So we know things that are about one human mass, and as technology expands, we can go to see the very small, and we can go to see the very large. But things on the very small are more typically dominated by quantum mechanics, and things on the very large are more typically dominated by general relativistic Einsteinian cosmology. And these are things we don't usually see much of on our human scale. So we're expanding into realms that we're not familiar with, and we see things that we just don't completely understand. So the size of the universe, we don't have a lot of information on the real size of the universe. We know, given the finite speed of light, the observable universe, we can look at things in the observable universe, but when you talk about the entire universe, that's out past the observable universe, and science hits a frontier. We don't know. We don't know things in the very small. They're too small for us to really understand. We don't know things on the very large. It's just too big to understand. But as the science progresses, as telescopes like Webb are able to understand more and see out further, we get to understand more and more on scales that are different from our human scale that we understand the best.
Let me ask you this. I don't remember reading this in the book, so I hope I'm not putting you on the spot. But, there are some cosmologists who think that our universe is one of many, that there are other bubble universes bouncing up against each other. And I wonder if you've thought about the possibility that dark matter, dark energy that we detect or suspect is here might be in something that's next to our universe.
Well, we detect things that are in our own universe. What's great is once you realize that there's other things out there, it leads to a tremendous amount of speculation, and which parts of speculation are true or untrue are only uncovered as we understand more and more about science. So whether there are causally disconnected universes out there, like we might be in this bubble, sort of like Earth is a bubble and then Mars is like a separate bubble, although we're not outside each other's universes, we're sort of in our own little bubbles. There might be a separately causally connected, disconnected universe, many of them maybe out there. But we don't know that for a fact. It's just tremendously fun to speculate, but we don't have any specific data that says that that's really true.
You're a sci-fi fan, I know, so I'm sure you've thought about this, and you do go into it a little bit. Retrocausality. So I have some physicist friends, and we do chat back and forth about the idea of retrocausality, and some of them think that events in the future can affect the past, that retrocausality is real. Where are you on that one?
Yes, no, I believe that there is something called retrocausality, but it does not allow you to communicate with the past. But things you do might affect the past. And it's really strange, and it takes me several chapters in the book of doing little bits of concepts here, first this, then this, then this, to build up to that. But basically, so if you have some experiment that happens somewhere, and then two particles go out, and you measure one, and then the other particle is really far away, what you measure can be correlated with what is measured for that other particle. But you can't communicate that because what you measure for your particle is essentially random, and what the other person far away measures for their particle is essentially random. But when you get together later, when you send out a signal at the speed of light saying, here's what I measured, you can determine that there was a correlation. And people wonder, how could there be this correlation? It seems like these particles must have been communicating faster than light. And not only that, but since I measured this in a certain way, it seems that the way I measured it seems to correlate with that faraway particle. And that faraway particle could have been measured in the past, not even now. And so it seems that something I've done now seems to have affected the past. But it doesn't allow communication in the past, because what happens is now we measure something random, and in the past they measure something random, and only later do we look at the correlations and we say, oh, wow, they're oddly correlated. But since it seems random to the people in the past and what we see, it doesn't tell us anything. It's like noise. We see noise. We think, maybe this noise is telling us something, but we don't have a key to understand that. And the only way we know to get the key is to send it at light speed. And when you do that, you can't communicate with the past. And I go to some effort to explain this little bits at a time in the book. But retrocausality is a fascinating concept. And not everybody thinks that there is retrocausality. There's many physicists who think there are, and there are many physicists who think there are not. They think that possibly we just live on the billiard table of life, and the balls are just bouncing into each other, and it was all predestined from long ago. And so what you're seeing and what happened in the past are all part of a causal chain that you just didn't know about before. So these are two things that kind of fight. There's the predestination on one side, and there's the retrocausality on the other side, and they kind of fight. But we haven't been able to come up with any experiment that distinguishes between the two. They all are consistent with modern quantum mechanical prediction.
Robert, the sci-fi fan, would probably enjoy the idea of time travel, us going back from now and go see some dinosaurs. But Robert, the scientist, has doubts about, you just said, we can't communicate with the past, so sending a person back there seems even more unlikely, I guess, right?
Yeah, so we don't know of any way to send information. If you send a person back, they would have information.
Yeah.
And we don't know of any way to do that. The only even in retrocausality, the only thing that's sent back is information that's not a message. It's just something random that only later can be correlated. But the science fiction, Robert, would love to speculate about that. And if for some reason you could walk into a time machine in your basement and come out a year later, then, as I point out in the book, you can just do anything for a year, maybe invest in the stock market, that's the quote future unquote stock market, and become rich. But then if you go across the street and then after 1 year passes, so you went into your time machine, you went back a year, then you waited out a year, and then you come back, then after 1 year later, you're at a different place, you can say, okay, information then had to go from where you used to be when you went into the time machine to where you ended up later instantly. So instantly means faster than light. So if you could go back in time, then you could communicate faster than light, but we don't know of a way to send people back in time.
Darn it.
I did a research project before about looking for time travel, and I got a lot of some email from people who really wanted to know how to go back in time, and I had to tell them, I'm sorry, I can't tell you how to do that.
We're having fun with Robert Nemiroff about his book, Faster Than Light, Big Questions, Fun Answers, Faster Than Light, How Your Shadow Can Do It, But You Can't, by my guest, Robert J. Nemiroff. A lot of fun. The book is fun. These topics are fun. I don't know if you recall at the top of this broadcast, I mentioned about an article that we posted in our news section tonight on the Coast to Coast website. It's about the discovery of what scientists think is a mirror universe. This was done by Professor David Hall from Amherst and a couple of his colleagues. The discovery was actually made a couple of years ago, but they just put some of the pieces together. I don't want to put Robert on the spot, but I'm going to ask him about that. Then we'll go to the phones, see what's on your mind for my guest here on Coast to Coast AM. Robert, not to put you on the spot here, but I mentioned about this article that we had posted tonight about a mirror universe that quantum researchers think they've discovered a doorway or something. Does that ring a bell with you, or you'd rather pass on that one?
Oh, it might surprise you and your audience to know I'm a bit of a skeptic on many things. So I don't know a lot about that specific claim, but I've heard previous claims sometimes by some pretty prestigious physicists. But in my experience, they just don't pan out. I mean, it makes for tremendous reading and makes for great speculation. But at the end of the day, the universe is strange in different ways than that. So unfortunately, I don't know it that well, but similar claims I've never been convinced of in the past.
I'll send it to you afterward, and maybe we continue the conversation another time. As I mentioned, You're a big sci-fi fan, so you know about Star Trek and Mr. Sulu, pop it into Warp Factor 9. We don't have that
Yeah.
capability. I don't know that we ever can have that capability. You write that, mass doesn't travel that fast, and we don't know a way to make it happen. Is there some kind of an engineering solution that you could foresee, some of the more exotic kind of propulsion technologies that are imagined? You write in your book about things that are inside of something else can travel faster than the speed of light.
Well, if you have a particle or you're in a spaceship that enters water, it will slow down quickly, but the speed of light in water is less than the speed of light in air. But if you have a particle or a bullet that goes in water, at first it goes faster than the light in water. And then what happens, it causes the water particles to jiggle and it emits something called Cherenkov radiation. But so that's not against the laws of physics. It's just that light slows down faster than other particles. When light enters water, it immediately slows down to less than it is in air. But other things don't slow down that fast. That means if you had a race down the swimming pool between a proton, say, and light, the proton might win. Particularly, there's a particle that goes through water very easily called a muon. And a muon would easily beat a photon down the length of a pool of water. So one thing, though, you reminded me of is that there are ways to go out into the universe. You can go even to a star 100 light years away in your lifetime. So Einstein's special relativity allows that with length and time contraction. So when you go fast, when you go compared to Earth, then the universe in front of you shrinks up so that you can actually go hundreds of light years away in your lifetime. And then you can stop and you can come back. And when you come back, you would find what's commonly called the twin paradox. It's what you would see in, let's say, Planet of the Apes. You would come back and you would find that Earth has progressed far into the future. Maybe humans have now somehow seceded into apes, but you're just a few years older than you were. And that's a well-understood effect and has actually been tested by putting atomic clocks in airplanes and flying them around on a very small scale. The atomic clocks come back and have recorded less time than the similar clocks on Earth. So you can do what is essentially warp 1 or warp 2 in your frame. Now, here on Earth, we would see the spaceship. We wouldn't see it go faster. We would say, it took about, at fastest, at most, it took a light year. It took a year for it to go a light year away. But if you're on the spaceship, you say, no, I can do that. If I have the technology, I can go to a star 1 light year away in just a few minutes. So we can go out into the universe with technology and see things that are light years away. And that seem like warp speed as shown in Star Trek. And it doesn't violate the laws of physics. It's predicted by Einstein's special relativity, but it's slightly different than depicted in Star Trek. The universe is a strange place, and it's strange in strange ways. And so sometimes these ways aren't convenient for science fiction stories, although there are some really great science fiction stories that do incorporate the correct special relativistic effect. Star Trek just seems to jump into warp speed, meaning that it's superluminal in everybody's frame, faster in everybody's frame. But so far as special relativity is concerned, you can go warp speeds, but when you come back, the Earth has progressed much further than it's shown in places like Star Trek and Star Wars.
I've read some interesting papers written for government programs where they speculate about warp drive and how it might work. They speculate about wormholes as being shortcuts. Any thoughts on those? You think that's pretty far out there?
So again, the skeptic in me comes forward and says, yeah. So there's this a lot of discussion on the web about something called the M drive that supposedly NASA's creating. But so when I've checked into that, I don't see anything I find convincing, and they never seem to come up with anything that shows anything definitive. So when you come up with a new theory, you have to convince the scientific community that what you came up with is true. So what you do is you make predictions. You can say, well, if you take these observations, you would see this, which modern theories don't say. And so you go and you look and you see which way it is. And things like that so far have not been able to out-predict what modern science, with its understanding of relativity and quantum mechanics, says. So it's fun to speculate again, but so far hasn't produced anything unexpected.
Let's take some calls. The lines are pretty full. We got Steve back here in Las Vegas on the West of the Rockies line. Steve, what's on your mind?
Good morning, gentlemen. Yeah, I did have a question and an observation. Starting with that, using the example of like sticking your hand out the window of a moving car, you feel the air pressure, which is invisible, pressing against your hand. So using that context, is there something in the vacuum of space that prevents the speed of light from going faster than the speed of light? Something that we haven't acknowledged or been able to measure yet. And the other observation I had was you were talking about increasing the speed of light by taking a laser, shining at the moon, and then moving the laser slightly so it goes from one side of the moon to the other would exceed the speed of light. And I liken that to like taking again, that goes under the assumption that the light is a solid beam that can't be bent. Now, what I'm thinking is that if you take a garden hose with a constant pressure, fire it at the side of the wall of the garage, the stream is constant, but it creates the illusion of bending. So whatever comes out of the end of the hose on your end will basically reach the other side of the garage, but it's still traveling at constant velocity, and I say the same thing with the laser beam.
Well, Steve, actually, Robert has some interesting experiments or proposed experiments in his book. Robert, you want to tackle that?
So basically, I would agree with almost everything that caller said, which might surprise the caller. So first of all, let's talk about if you have a garden hose and you have a wall and you can move the water, leaves the garden hose at less than the speed of light, but it can create a wet spot that moves across the wall faster than light. But that's just the unrelated superposition of water molecules hitting the wall. It's not, at no time does water ever go faster than light. So this is just an effect that appears that way. But you're right, you had a really good example. Also, the first part of your question was, does vacuum, is light related to vacuum? Yes. So also, when you take, one other digression. When you take a laser beam and sweep it across the moon, the light from the laser beam never goes faster than light. It always goes at exactly the speed of light. It is the spot on the moon, which is the unrelated superposition of where those photons are hitting, just like the garden hose water hitting the wall. It is the unrelated where those photons hit that appears to go faster than light. At no time does light itself ever go faster than light.
There's
the other really good point that was raised is, do you need vacuum to have light? And the answer is we don't really know. That's right on the cutting edge of science. There are people who make the Schornhorst effect, is that if you can change the vacuum, maybe you can very slightly speed up light speed. It might be that light is tied to the underlying vacuum of the universe, but we just don't know for sure. And these are topics of active research right now. So you've touched on something that's really fascinating, and it's a topic of research. We don't know the answer to everything. We don't know the answer to that one.
There's a fun scenario you write about in the book. I forget where it is in it, but it's an engineer on a train that's traveling at the speed of light, and he's got a ball in his hand, and he throws it forward. Does it travel faster than the speed of light?
Yes, that's a that's a very good question. It's a common question. So the train cannot pass you faster than light. And if the engineer throws off a ball that the engineer thinks is moving faster than the speed of light in the same direction, all we see is that ball moves closer to the speed of light, even though in the train frame that ball is moving close to the speed of light relative to this. We never see anything past the speed of light. So that ball could then throw off another ball that it thinks is moving close to the speed of light, and we would not see that go faster than light. That would only be much, much closer, infinitesimally closer to the maximum speed, the speed of light. So even if things keep throwing off faster things, we never see anything pass us faster than light. That's what Einstein said back in 1905, and that is what experiments continue to show today.
Yeah, whenever I hear one of those train kind of questions, it takes me back to math classes in high school, and I get scared about the whole thing because I know it's going to be something that's hard. East of the Rockies, Jimmy.
The concepts are simple, though. The math is a little complicated, but the concepts are simple. You just can't keep throwing things off. It just doesn't go faster than light. It just goes closer to light.
Gotcha. East of the Rockies, Jimmy in Georgia. Hi, Jimmy. You're on with Robert Nemiroff.
Hello, George. You're the greatest. Your music playlist alone is worth the price of admission. Let me give you an absurd premise, but I've got a serious question related to it, and I'd like a serious answer. A moon rover goes over the hill, and it finds a 1919 Ford Model T in pristine condition parked on the other side of it. And it appears to have been there since 1919. Here's my serious question, Robert. Would NASA tell us about it?
So,
Hello?
Yeah.
could NASA tell us about? So, not exactly clear on the question. So, there's a car that's been sitting somewhere that's from 1919 and it's still sitting there. Can NASA tell about it? So, I think I'm not giving justice to your question.
I think he's asking, would NASA, you had said NASA is transparent. Would NASA be transparent in finding something on the moon that doesn't belong there?
Oh, yes, in my opinion. And again, I don't speak on behalf of NASA. NASA would be immediately transparent on that. We don't, in general, NASA, to my knowledge, does not investigate cars that appear to have been sitting there since 1919 because we're more interested in exploring the outer universe. That would be more the Department of the Interior or something else. But if there was something unusual that was to occur on Earth, there would be people who would investigate it, and things would come out. If NASA's involved, almost always it would be very transparent. Okay,
I think Jimmy was dubious about that. We cover a lot of topics that touch on NASA here, and there are differences of opinion. I'll just put it that way. We're going to the wild card line. Brendan in Austin, Texas. Hey, Brendan.
Hey, thanks so much, George and Professor Robert. I'll be super quick. I wish I could ask about the Future Hadron Collider. And, George, the recent episode of Weaponized was fantastic. I'm looking forward to more.
Thanks.
Mikio Kaku said that society will change with quantum computing. And I know you said quantum mechanics doesn't affect the speed of light, but will quantum computing affect our ability to compute the superpositions, as you were just mentioning a little bit ago? And did you have a favorite UAP video that was that had been released, or did you see the Border Patrol ones? Have you seen with the Tic Tac one that it's really bright, and Ukraine says that they have black Tic Tacs? Or do you think that light could be used as a fuel or propulsion for the UAP?
Wow, okay, a lot of questions there. First of all, quantum computing seems to be a really great thing that's developing. It's ways of using quantum mechanics to compute that classical computers, the way most computers work nowadays, are just classical, and enables us to do things to solve problems that we were not able to before. Right now, quantum computing isn't really doing much for us, but it's all about potential. And quantum computing has a lot of potential to help us compute things in the future. You'll have a famous favorite. So again, the skeptic side of me says that when I see something I don't understand, it intrigues me to try to understand more. But so far, almost every time I've seen something like that, it just means that there's some kind of computer glitch that we didn't know about, or some kind of observation that is seeing some kind of glint or something that we didn't know about. So almost all, so far as I can tell, when we investigate something, it almost always has a non-supernatural explanation that is plausible. And even though it's more fun to assume the non-normal explanation, the skeptical side of me says, let's just go with the normal explanation first. I know that's not what this audience wants to hear, but you have to prove it. So as Carl Sagan said, extraordinary claims require extraordinary evidence. And so I need to see the extraordinary evidence for me to really believe some of those things are extraordinary.
Well, I would say that, that if there's evidence for it, then the claim isn't all that extraordinary to begin with. The Tic Tac case that the cases that he was talking about were not computer glitches. They were seen by the pilots. I think those have been investigated by our government, the UAP task force. They haven't come up with an explanation for it yet, but we are welcome to all opinions here. And Coast to Coast is used to hearing a lot on one side of it, but your viewpoint is certainly welcome, along with others. Bill in Los Angeles on the wildcard line. What's on your mind?
Hi, George. Similarly, I was wanting to get Dr. Nemiroff's opinion on how he accounts for the apparent 60,000 mile per hour speed of the Tic Tac Navy video and the pilot's own shock at what they were seeing. And how does he account for that data in terms of earthly physics, or can he?
Okay, so I'm not familiar with that case very much, other than seeing like a second or two videos on the web or TV. So I really can't address the specifics of the case. But many times, there's a lot of things that scientists see that they don't understand. For instance, one thing is like, I don't know why the laundry on the chair in the bedroom smells like root beer. I just don't know why that is. It doesn't seem to make sense to me. But I don't attribute that to a supernatural thing. I don't think that extraterrestrials came in and dumped some kind of chemical. I think that maybe my kids spilled root beer and didn't tell me, or something like that. So a lot of things we see in science we don't understand. But in order for it to be a supernatural explanation, we need to have verifiable results. We need to be able to reproduce it. We need to be able to predict something with it. And we have to be able to discount all the normal explanations. And I know that's not the audience. I think it's great fun to ponder these things, but my advice is to try to get even more extraordinary evidence and make predictions with it. Like, if this is true, then this must be true, and then we can go off and do that experiment.
Yeah, I think that's good. I think that's good advice. Robert, we're out of time here. Thanks for all of our calls. And Robert J. Nemiroff, Faster Than Light is a lot of fun. It's a heck of a good book and taught me a lot, and I hope you'll come back and share more of your thoughts with us down the road.
Yes, sure. Thanks for having me.
All righty. Thanks also to my earlier guest, Dr. Ray Boeche, and to my colleagues there at Coast to Coast, Donna Walker and Michael Cosio, Ryan Stacy, who bids us farewell at the end of the month, Dan Galante, Chris Boros, Lisa Lyon, Tom Danheiser, and, of course, George Norrie. I'm George Knapp. I'll be back in a couple of weeks, everyone. Talk to you then.